Alright, so today's lecture is on isomerism. Typically, what you'll be giving on an exam is a question that asks you to list all the constitutional isomers of a straight chain alkane that meets certain criteria. So the strategy, so you don't run out of time, is that you need to know the isomers coming into the exam, which sounds like a lot, but you'll see that it's not that bad. So the first is that you should commit this number to memory. So this sequence up here, 1, 1, 1, 2, 3, 5, 9. You'll see what it means in a little bit, but basically it tells you the number of isomers for each, I guess, length of carbons that you'll have. It makes more sense when you start actually looking at it. So what do we mean? Well, if you only have one carbon, there's only one molecule you could have, and that's just methane, just a lone CH4, just like that. Likewise, if you have two carbons, there's only one possibility. Once again, just connect them by a sigma bond and you have ethane. Similarly, if you have three carbons, there's yet again only one possibility, and that is propane, which looks like this. So you'll see already that the sequence, as we increase the carbons 1, 2, and 3, we get one isomer, one isomer, and one isomer. So now that we're on to 4 carbons, you should expect us to get two different possibilities. So if we're looking at 4 carbons, the obvious answer is a straight chain of 4, which you should recall is butane. And if you have a 3 carbon chain and you have a substituent coming off, you have what we'll call isobutane. You also need to know the IUPAC name, which would be 2-methyl propane. Alright, still not that bad. Let's look at 5 carbons. This is when things get a little dicier. So, 5 carbons. The first one, again, is the obvious 5 in a row, and that'll just be pentane. After that, you should try a 4 carbon chain and putting a substituent on, and you'll get isopentane, or what we could also refer to as 2-methyl butane. Notice that if you take this methyl group and put it over here, you might think you'll get 3-methyl butane, but the way that you number the chain will go 1, 2, 3, 4, and you'll see that once again it's simply 2-methyl butane. So that's an important point. Whenever you create a constitutional isomer on an exam, you should try to name it, even if you don't get points for it, because that tells you whether or not it's the same structure as something else. Otherwise, you might draw repeats on an exam. Next up, we have a 3 carbon chain with 2 substituents coming off the second point of contact. We'll call this 2,2-dimethyl propane. I should have a dash here as well. Okay, so as you'll see next in our pattern, we're at 6 carbons. We're going to have 5 different isomers now. And again, these have to be straight chain, well, not branched or straight chain alkanes, as long as there's no degrees of unsaturation. We'll talk about that in a bit. So the 5 isomers of 6 carbon length, the first one is again obvious, it's the straight up hexane. Then you shorten it once, and you have 2 different spots that you could put the methyl group. You could put it on the 2, or you could put it on the 3. So you have 2-methylpentane and 3-methylpentane. Likewise, if you go down to 4 carbons, you have 2 different possibilities. Put them 2,3 or 2,2. Notice again, if you try to do 3,3, that's actually going to be the same as 2,2 when you try to name it. So you have 2,3-dimethylbutane and 2,2-dimethylbutane. Okay, and if you'll remember our sequence, the last thing we need to know is that for 7 carbons, we're going to have 9 different isomers, and this is when it starts getting a little tricky, and this is why you gotta know them before going into an exam. So for 7 carbons, again, there's the obvious heptane. Then there are, again, 2 arrangements that have a hexane, so you could have a 2-methyl or a 3-methyl. Notice if you put it as a 4-methyl, that's actually going to be the same thing as a 3-methyl, because it will reverse the numbering of your chain. There are quite a few possibilities for chains. You could have 2, 2, 2, 3, 2, 4, 3, 3, or I'll add this one separately because this is the one people usually forget about. You can have 3 ethyl pentane, which looks like this. And lastly, if you modify that 4 carbon chain, you can have 2, 2, 3 trimethylbutane. Okay, so at this point, if you're in Rutgers 307, what you should do is you should make a list. You should literally copy these isomers off this video and make a grand list. You need to know all of these and their names going into an exam, and I'll show you why momentarily. So again, have all these down, be comfortable with generating them. Okay, now let's actually solve some problems. So, what you could expect to see on exam is something like this, and it'll be worth 10 points. So it says, draw all the compounds of the molecular formula C7H16, and longest chain has 5 atoms. So here I'm going to tell you that there's an algorithm when solving these isomer problems. The first is calculate degrees of unsaturation. You may or may not know what that means from a previous video, but I'll explain it again briefly. The second thing you want to do is draw all isomers of appropriate chain length. Once you've done that, modify with accordance to problem. Okay, so degrees of unsaturation. So there is a formula that goes something like this. DOU equals 2 times the carbons you have plus 2 minus H minus X, I believe, plus N all over 2. What this formula does is it calculates the number of double bonds, triple bonds, and rings you have. So what that means is that if you have a degree of unsaturation, means you have a ring or double bond. 2 degrees of unsaturation means you can have combinations. So 2 degrees can get you a triple bond, it can get you a ring and a double bond, it can get you 2 double bonds. But basically, what we care about is if degrees of unsaturation is greater than 0, this strategy will fail. So everything I'm about to tell you about solving these problems won't work if your degrees of unsaturation are greater than 0. The reason is that if you look at all the structures we've generated so far, all of these and all of these, there are no double bonds, triple bonds, or rings anywhere. So if you have degrees of unsaturation greater than 0, that means the possibilities include rings, double bonds, and triple bonds. Okay, so the first thing you do when you start this problem is you make sure your strategy could work. The way you do that is you use this formula and you see if you have DOU equal to 0. So here we have C7H16. So we do the calculation there. It's going to be 2 times 7 plus 2, which is 14, plus 2 is 16, minus 16 for the hydrogens. So you should have already said that that's 0. When you divide by 2, you get 0 anyway. So degrees of unsaturation equals 0 means we can continue on. Okay, the next thing it says is we have a C7H16. So immediately, since you've memorized these at the point of the exam, you quickly draw all of them on your paper, just like that. And then you look at the requirements. So this problem is asking for longest chain has 5 atoms. Okay, well that makes it rather simple, doesn't it? Because this is a hexane, so its longest chain is 6. This is a hexane, so its longest chain is 6. This is a heptane, so its longest chain is 7. And this is a butane, so its longest chain is 4. So if you're on an exam, what you have to do is you have to draw these 5, give their names, and you get 10 points. Don't spend 30 minutes on these problems when you can walk in prepared and do them in 3 or 4. Let's look at another example. So this will be similar, and it'll be worth 12 points. So it says, draw and name the isomers of C7H16 that have at least one tertiary carbon. And again, we already know, since we did this calculation, that degrees of unsaturation equals 0, so our strategy is fine. Once again, since you've memorized these isomers, you quickly draw all the isomers that are of the appropriate length, which in this case is 7. And now we're looking for tertiary carbons. So heptane has a primary carbon here and a secondary carbon here, so it doesn't actually have any tertiary carbons, so heptane's out. 2-methylhexane has a tertiary carbon right here. Remember, a tertiary carbon is a carbon connected to 3 other carbons. Similarly, 3-methylhexane has a tertiary carbon here. Over here, 2,2-dimethyl gets a little bit tricky because you have a primary, secondary, then don't be tricked by this. This is a quaternary carbon, which is a carbon connected to 4 other carbons. So there's actually no tertiary carbon in here. This has a tertiary carbon right here. This has a tertiary carbon right here, so this structure is good. This has a tertiary carbon. This is, again, like 2,2-dimethyl. You have a primary, secondary, and a quaternary, but no tertiary. Over here, you have a tertiary carbon, and over here, you have a tertiary carbon. So to get your 12 points, you would have to draw these 6 and name them. Again, it's simple if you come in knowing all of these isomers, and you could quickly work through the list and eliminate the ones that don't work. Okay, so let's look at something slightly more difficult now. So sometimes what they'll ask is they'll ask for slightly different alkanes. What I mean by that is they'll put a functional group on there, and then they'll expect you to do the problem. So here, once again, it's asking us to do line angle formulas with isomers of C5H12O that have an alcohol group, so an OH bond. So the first thing, once again, is do your degrees of unsaturation calculation. So that's going to be 2 times 5 carbons plus 2 minus 12. The oxygen isn't in the DOU formula, so we don't have to worry about it. And once again, you get 0. So our strategy is going to be valid. The next thing we do, since this is a C5, you're going to, from memory, introduce your 5 carbon compounds. I'm actually going to put them vertically. You'll see why in a second. So this is what we're starting with here. And now we want alcohols. So facts you should know about alcohols. So alcohols are terminal. You cannot have an internal OH and consider that an alcohol. So what that means is that all we need to do is modify these structures that we have and basically just put an OH wherever we'll get a different name. So an example of that is with this top structure, if you put the alcohol on 2, you'll get pentan-2-ol or 2-pentanol. Either, I guess, naming will work. And if you put it at 3, you'll get 3-pentanol. I guess you could also do just vanilla old pentanol, which I forgot to draw on my lecture notes. So over here, it gets a little trickier because you have more points of attachment. And here I suggest whenever you add it to a spot, make sure you have the name to make sure that you don't double any. So if we add the alcohol to the end, we'll get this 3-methyl-butan-1-ol. So the way that works is that the alcohol has higher priority, so we name it starting from the side with the alcohol 1 and ending over here as 4. We also can put the alcohol on the adjacent spot, and that will get us the 2-butanol, or the butan-2-ol. Then we move it once more over. Don't get tricked by this carbon here. Remember, it's tertiary, so there's one invisible CH bond that we could replace with an OH to get that. And lastly, if you move the OH one spot over, you'll realize that it's not in fact the same as one of the previous structures you've drawn, and you could actually make 2-methyl-1-butanol. then lastly, pentane, you'll see down here that each one of these C-C bonds is symmetric. So remember, you can't put it here because that'll give 5 bonds to carbon. The only place you could put it is on one of these carbons over here. No matter where you put it, you'll get the same thing. Okay. So again, if you didn't start with these, it would take you a lot longer to generate all the structures, and you might forget one. Okay, let's try another problem. So the other thing they could, I guess, give you that's a little trickier is they'll ask for ethers. And ethers are a little different as well. But let's stick to our algorithm. So again, our degrees of unsaturation formula gets us 2 times 4 plus 2 minus 10 over 2. That's going to be a 0. So our strategy is going to be fine here. And then we're asked for C4. So I'm quickly going to generate those. So our C4 isomers are butane and isobutane. So ethers are a little tricky. The thing with ethers is that ethers are internal only, so you can insert the oxygen between any 2 carbons. So this red dot, I'm saying let's insert an oxygen there, and that will get you this structure. So between this carbon and this carbon, this carbon and this carbon, I inserted an oxygen, and that got us this ether. Similarly, let me move this over. If we insert an oxygen in the middle over here, we can form another ether. And you just gotta keep doing this from the isomers that you came up with. So this is also symmetric. If I insert here, I'll get the same structure. And if I insert an oxygen over here, I'll actually generate the same structure as this. So let's try something again, slightly more difficult. So you see the utility of this strategy. Isomers of C5H12O that do not have an OH bond. So it has an O and it's not an alcohol. That's another way of just saying it's an ether. Degrees of unsaturation calculation says 5 times 2 plus 2 minus 12 over 2 equals 0. Our strategy is fine. From memory, draw the 3 isomers of 5 carbon, and at this point, look for locations that you can modify them. So if I insert an oxygen here, or here, or here, or here, or here, or here, and if you do that, you will generate, well, you should try on your own first to see if you can draw the structures. They're a little tricky because you got to elongate some of these chains, but if you want to check your answers, it will look something like this. Okay, so again, to recap, the way to attempt these isomer problems is walking in, knowing the given alkane isomers for these, I guess, number of carbons, and you could remember it easily how many you need to generate with this sequence. So if you memorize all of these coming in, what you could do is just use a simple strategy where first you calculate DOU to make sure that it's 0, then make sure that you don't have double bonds or ring isomers included. Once you've done that, you simply remember the isomers that you memorized and then eliminate them or modify with functional groups based on what the problem is asking for. Now, I haven't gone over all the functional groups here. What you should do in your free time is figure out what you do with amines, so that's nitrogens, and carbonyls. Those haven't been asked on exams in the past, but they're not too different, so you could see those in the future. The other thing is, I recommend if you do get a degrees of unsaturation greater than 0, you save that problem for last on the exam, because there's no quick algorithmic solution. You're going to waste a lot of time trying to solve that problem. So do every other question on the exam before you attempt an isomer problem that has a DOU greater than 0.